Well, it's a bit strange to talk now about isolated bridges because we haven't yet discussed about isolation. But since the decision was to anticipate most of the material related to bridges to today, I will try to discuss the main issues without entering in any detail about the characteristics of an isolator or the sorts of things that will be discussed tomorrow. I will also use this opportunity just to show that there are structures for which it is simply not possible to design using a force-based approach. And isolated structures are certainly one of these cases. Now, just to anticipate only a few issues, but we need at least a few points to make a few points, we have to consider what are the main purposes to decide to isolate a structure. This is not exactly what is commonly intended, because years ago when they started with base isolation, probably there would have been only one main point, which is not even mentioned here, which is just essentially to elongate the period of vibration of the structure to reduce the acceleration and therefore to reduce the strength demand on the structure. We will see tomorrow that, of course, doing that you are also increasing the displacement demand and that there are a series of problems that have to be faced. So what I would prefer to point out is that we discuss about using an isolation system for other reasons. One reason is certainly to protect the structure in the sense that the isolation system will be used essentially to control the maximum force in certain area of the structure and therefore to make it easier to apply capacity design principles. This can also be obtained through something which is not exactly a base isolation, but for example is an added damping, which is in a general sense considered to be in the general area of isolation and added damping, which implies in a way that you are reducing the displacement demand, as we have been discussing today, and therefore you are reducing the action. And when the second point there, which is shifting the main period, we have to underline to modify both acceleration and displacement demand, and keeping the displacement demand within reasonable limit to increase the global energy dissipation, and this means to reduce the displacement demand. But the last point is probably one of the most relevant for bridge design, which is to regularize the response. And I will try to discuss conceptually this point with reference to the examples that Nigel has been presenting in the previous lecture, just to show that it is possible in principle to design some sort of isolation system for a bridge in such a way that the response becomes very regular, and therefore everything is much easier, not easier only from the point of view of calculating the structure, but easier from the point of view of the response of the structure that becomes more acceptable because there are not concentrations of demand in one pier or in another one. This is the only other slide related to general points. I would like also to point out that when we are talking about isolation and added damping, we could talk of very different problems. So probably the first figure in the upper left corner is the only one which is normally considered the base isolated structures. So you are designing an isolation system for a building which can be stiff or less stiff, or for some structure that could be a nuclear reactor or whatever, and that's a real base isolation. But if we are talking about bridges, which is what I will be discussing starting from the next slide, the common thing is to have an isolation system at the deck level. And this makes the structure response completely different, because of course the piers are not isolated. And if you think to the structure in general terms, in the direction of making the response more regular, you could even conceive something where you are not isolating all the piers, because you want to use the isolation also to make more flexible the foundation pier systems that are more stiff. In such a way, the displacement, the deformation of the deck will be much reduced. The deck will not be cracking. The reaction at the abutments will be controlled and so on. But it is also important to mention that there are other kind of isolation system. There is an isolation system that has been applied, and this is something that in any case I will discuss tomorrow, not today, is the fact that you could have a kind of a rocking bridge pier. A rocking bridge pier is essentially an isolated pier, because when you have the possibility for one leg of a frame pier to raise up, it means that the force, the shear force, cannot increase anymore, actually should decrease, unless there is some tensile capacity at that level. So this is another kind of very interesting isolation system that could be used for bridges, but could be used also for other structures when you accept to have some rocking behavior of the whole structure or of part of it. I will also mention the fact that there could be other kind of systems that are adding damping and controlling the response, such as internal bracing that are dissipating energy. But there are also unconventional base isolation system. For example, having some sort of controlled layer of sand and gravel at the base of a structure that could well be a bridge pier, and actually it has been used in at least in one case of a very large bridge, in such a way that for a certain level of excitation there could be some rotation at this level, and there could be also some relative displacement at this level. In this case, of course, these piles are not connected to the base of the pier, to the lower part of the pier, but there is a complete disconnection where the pier could move. So it is a complex problem, and now I will only focus on the most common issues, and then I will discuss a very specific case of deck isolation, which is the case of a cable-stayed bridge. A cable-stayed bridge is a natural isolated structure in the sense that the deck can be completely disconnected from the pier, and therefore can respond essentially as a real pendulum attached to the top of the pier. Of course, in that case, you may have a very large displacement, and therefore the problem becomes to control this relative displacement. And I will try to show conceptually, but also with a real design case, how this problem could be dealt with. So going back to the example that Nigel has been using several times, I would like first of all to point out something that has already been mentioned, but I think it's worthwhile to repeat it and to take advantage in a more complete form of this. If you have an irregular bridge like this, what you are normally trying to do is that you are considering each one of the systems made by soil, foundation, pier, and to try to see how this system responds, and therefore to be able to somehow represent this system with some sort of spring that could be linear or nonlinear, but is a spring anyway, and should be also characterized by some equivalent damping. And of course, this could be true also for the abutment, for this pier, for this pier, for this pier, for this pier. Nigel has been showing that if you consider the longitudinal response of this structure, you are somehow assuming or forcing that the displacement at the top of each pier and at the abutments, the deck displacement is the same. So it has been discussed that if the displacement is the same, certainly the ductility demand at the different piers is different. And if this is the case, clearly it doesn't make any sense to define one single force reduction factor that should apply to abutments, piers, and everything. On the opposite, it is clearly easy to define the property of each one of these systems, and if you think in terms of displacement-based design, the parameter that you will use for each one of these systems, and then you combine to have something which is equivalent to the force reduction factor in a force-based approach, is essentially the equivalent damping. That's why I wrote down this equation in such a large letters, because the problem there is to find out what is the global value of the equivalent damping of the structure, considering the different parts of the structure. And the different parts of the structure could be combined in something that is similar to a combination of springs in parallel or of springs in series. So if you consider one of the systems made by soil, foundation, and column and pier, what you immediately note is that essentially the same shear, the same force is passing through each one of these elements, if you forget about the mass of the pier, of course. So you have the same forces passing through, and you have different displacements. What this equation is telling us is that essentially the global equivalent damping is somehow proportional to forces and to displacements. And this is obvious. Why is obvious? Because the equivalent damping is essentially proportional to the area of a loop, and the area of this loop is proportional to the force and to the displacement. But if you are combining two elements and they have the same forces passing through, then in this equation the forces are disappearing, and you can write that the equivalent damping is just proportional to the displacement of each one of the elements that you are combining. So you can find out what the equivalent damping is of a system made by soil, foundation, and pier, just considering this equation and making the global damping proportional to the damping, not proportional, sorry, equal to the combination of the damping of each one of the elements multiplied by its own displacement, taking the sum and divided it by the sum of all the element displacements. But you immediately understand that the same thing is true if you want to evaluate what the global equivalent damping is of a system of different piers. In that case, what happens is that if you look at the longitudinal displacement of the bridge, you have the same displacement instead of having the same force passing through the different elements. And then, if this is the case, it means that the global equivalent damping of the bridge is the combination of the damping of each one of the systems multiplied by the force which is going to that system and weighted on the global base shear. In a way, I'm saying that while it is totally irrational to try to find a single force displacement factor, force reduction factor, it is totally rational and physically sound to find a global equivalent damping, which is a factor that reduces the global displacement of the structure. If you want to look at this in physical terms, what I'm trying to say is that if there is a single pier which is taking most of the shear, then the damping associated to that pier is dominating the response with respect to the other piers. And if in a pier there is one of the system which is taking most of the displacement, then that element is dominating in the evaluation of the global damping of that pier. This is important because, now I will go to isolation, but isolation means to have some element where you have some concentrated displacement and you have some well-defined damping, because the damping is something which is connected to the nature, to the essence of that element. If you add an isolator on top of a pier, and the pier is flexible, therefore the total displacement is going more to the pier than to the isolator, then the damping associated to isolator has a little effect on the global response of the structure. That's why it is much more effective in terms of added damping, an isolator, a deformable isolator on top of a stiff pier than the opposite. Because you want to concentrate the nonlinear response on the isolated, and therefore there is where you have the damping, and there is where we want to concentrate most of the displacement. Now, let's go and try to see more what happens, and this is also a slide that has already been used, and actually when Nigel used this slide, he was not talking about an isolator here, he was talking just about a bearing. So what happened here? What happened was that in the evaluation of the total damping of this structure, you were designing the bearing to take the force that has to pass there without any significant nonlinear response. And therefore, if you were looking at this structure as a whole, most of the nonlinear behavior, of all the nonlinear behavior, was in the pier. So you were combining a nonlinear response with dissipation in the pier, and you were having some linear response at the bearing level. And you could see the same thing looking at the fact that this displacement here, which is the displacement at this level, remains the same. Why remains the same? Because the pier is going to yield. When the pier yields, the force is not growing anymore, and therefore you cannot have at the same time a plasticization in the pier and in the isolator. You can have only one of them if you accept, as it is rational to accept, that the same forces is passing through the elements. Now, what happened in this case is that if you wanted to evaluate the global damping, the equation that I was showing earlier, you see here, is just as a function of the displacements and not of the forces. But what you would also note here is that this global damping is essentially dominated by the response of the pier, which is where you have the larger part of the displacement and where you have the larger part of the energy dissipation. Now, looking also at one of the last slides that Nigel was showing, the problem of the transversal response of a bridge, possibly of a very irregular bridge, something where you can have some short pier in the middle, and therefore, or in the middle or on one side like here, and therefore you are somehow making some error when you are trying to guess what the top displacement should be here. Now, if you look at the problem like this, it would make sense to try to design an isolation system where you had more flexible isolation devices on top of these two piers and less flexible isolation devices on top of the taller pier. If you do something like that, you can try to have a response of the structure where the different piers, or actually foundation pier isolation system, have globally similar characteristics in terms of strength and displacement. So instead of having something like this, you maybe add also some isolation device here and here, and if you look at the displacement shape from the top, as you do in this plot here, the deformed shape of the deck can be similar to a straight line. Okay. What I mean is that the response, instead of being what I was showing here, where you had the nonlinear response in the pier, is something of this sort, where you have a linear response in the pier, and you have a strongly nonlinear response at the isolator level. And instead of having something where essentially this part here was remaining close to B constant, you have this part here which is close to B constant. So this is essentially the difference that you obtain when you use an isolation device instead of using a normal bearing. And let me say that very often an isolation device costs less than a standard bearing. I could prove this, of course. So what I'm trying to say is that to use isolators instead of bearings, in most cases, ends up with a less expensive system, even considering just the isolation system. In a case like this, again, it is straightforward to guess what the equivalent damping of each one of these pier isolation systems will be, but the target will be to do something like this, which means to have isolators here, or isolation systems if there is more than one, where you end up having some global response which is very similar one to each other. This would imply, in principle, that each one of the isolator on top of each one of the pier will be different. And you will never do that in the real world. In most cases, you are going to have maybe two types of isolators. Or maybe what you could do is that you could use only one type, but you could put 3 isolators on top of a pier and 2 isolators on top of another one, or something like this. So I'm not saying that you could reach perfection in the design phase, but you could get closer to a structure that behaves in a better way. And of course, it is then the case, as Nigel was also pointing out, that you go for a nonlinear analysis of the structure, but this is a kind of a spatial nonlinear analysis, because all the elements will behave in a linear way, with the only exception of the isolators. So if you do a model like this, you have only maybe 5 nonlinear elements with a bilinear response, which is not certainly a complex model to be prepared and to be run with any sort of time history that you want to use. So this is essentially the basics of the isolation of a bridge. And now I would like to show you some more realistic example, because I think that this will be helpful to understand the whole thing, but also because it is 20 minutes to 5, and this will be maybe less demanding in terms of attention and so on. So first of all, maybe not, maybe it will be demanding. So first of all, I would like to talk about cable-stayed bridges. I like cable-stayed bridges very much. They are very, funny structures. So when you start with a cable-stayed bridge, of course you don't start from the seismic design of a cable-stayed bridge. You start from the global dimensioning, and of course you start with gravity, because after all the bridge has also to cope with gravity. And if you look at the literature, with the exception of a recent paper that I published 2 months ago on this subject, there is a lot of material about analysis, about how to deal with resonance of cables and so on, but it's very unusual to find some indication on how to design a bridge. So first, what we do normally, and forgive me if I go with simple things. Well, first of all, you start from geometry, and maybe you look at the requirements that your client is giving you, and normally the requirements are only essentially two things. It's just the span, and is the height above the sea or the water level, because you have to pass there with a ship or something like that. So based on this, you try to have a first guess on the geometry, which means to dimension the total height of the tower essentially as a proportion to the span that you need to have. And maybe what you will do is to have something where the height of the pier is maybe in the range of, say, 25% of the span or something like that. For example, and I will continue on putting figures to make the things less heavy. And for example, if the span is 415 meters and the height of the deck here is 60 meters, maybe you end up with the height of a tower which is in the range of under 64 meters, maybe. Then the next thing that you do is possibly the fact that you want to see what is the level of axial force in the deck. And in that case, is rather simple, because in the average, you have a cable at 45 degrees. So essentially, you have a similar value of compression in the pier and of compression in the deck. And after that, maybe you will try to size the beams, the longitudinal beams, for axial force. And if you go ahead with the figures that we were using earlier, and you assume a certain weight of the deck, for example, 2 tons per square meter, including the live load, you end up with something where you have a dimension, a section for the longitudinal beams, and this is just for axial load, not for flexion. And then maybe you try to dimension the size of the cables, and again, this is not too difficult, because you will set up a distance between the cables, so you know what is the weight of the deck, and you end up with some sort of average figure. I'm saying average because you have different forces here and here, but for the time being, you only want to know what is the amount of material that you need to put there. And we are now still with gravity, but we're getting closer to the real problem of designing this bridge for earthquake. And I'm saying that we're getting closer because we're starting considering the fact that you could have some eccentric gravity load due to live load, essentially. And because of that, you are certainly going to have some bending moment and shear at the column base, at the pier base. This will depend also on the capacity that the deck has in terms of continuity to reduce this moment. But even considering gravity in this case, you will immediately realize that you are also going to have a different compression in the deck on one side and on the other, because on one side you have more weight, on the other side you have less weight, so you have a different stress in the cable. So if you don't do anything else, what will happen is that the deck will move. And you need to go to large displacements in such a way that you find again equilibrium. You cannot solve this problem in small displacements. And if you do some calculation, you end up with some moment demand at the pier base. Now we come to the real problem, and the problem is, are we going to have some connection between the deck and the piers, or the deck and the abutments? And here we really start with the seismic design, and here we really start where I don't think that there is any rational way of doing some preliminary design without starting from some displacement-based approach. And what I will discuss now also applies to the problem that I just mentioned 1 minute ago, because if you have some connection, you are going to reduce the displacement that you need to equilibrate the different axial force that you have in the deck. So what can you do? Well, if you accept to reason in terms of displacement, what you will do is what we've been discussing this whole day, which is to decide what longitudinal displacement you consider acceptable for this deck. And this is now something that could be related not to strictly earthquake problems, but could be related, for example, to the problem of joints at the end of a bridge, to all sorts of problems. But anyway, you should start from there and say, this is the level of displacement that I accept. For example, let's assume that we will be accepting 1 meter displacement. If you do that, then of course it's easy to have an approximation of the total mass. And at this point, since you are assuming that at the end you are going to have some sort of connection between the deck and the piers or maybe the abutments, you should also assume some level of equivalent damping, because these connectors that we will see at a later stage will be dissipating energy. Of course, you could also have connectors that do not dissipate energy, but it will be not an intelligent way of facing this problem, because if you are going to dissipate energy there, you are reducing the relative displacement, and therefore your structure will be a more efficient structure than if you use something where you don't have any energy dissipation. So you now have an assumption on the energy of the equivalent damping, and you have assumed some displacement, so you can enter a spectrum, and you can end up with an equivalent period of vibration, and this equivalent period of vibration in most cases is a rather long period of vibration, because you have a structure that behaves essentially as a pendulum. And now it's a rather long process in terms of steps, but just to make it clear, so you can determine the required effective stiffness and the base shear. And I'm going ahead with the numerical examples that I was considering earlier. And then you should see what fraction of this shear will go into the cable and therefore will be a shear at the top of the pier, and what fraction will go at the level of the deck. And if you do that, you may end up that you do not need a force transmission, or that you may need some force transmission. But you end up with a certain level of bending moment, and you will compare this bending moment with the bending moment that you had calculated for gravity at the base of the pier, and you will see whether the base of the pier will be able to take that gravity moment or not. Then continuing on, we know that we have a certain level of displacement, and what we want now to do is to see what will be the properties of the damping system, the connecting system between the deck and the piers. And this, of course, these properties are those properties that will give us that 30% equivalent damping that we were assuming. If we cannot do that, we have to change the damping and to repeat the design. Now, if you want to do something like that, you use the standard equation that I was already showing. In this case, you remember we have the same displacement, so we use the force. We have to check what level of force is going through there. And you come up with a certain level of force. And if you use certain kind of damper, this is something that we will discuss tomorrow. This is done here, assuming that you use hydraulic dampers. Hydraulic dampers has essentially only one parameter that is defining their properties. It's the C parameters that we will discuss tomorrow. Don't mind too much now, but you are defining what kind of force and what kind of property your isolation system must have. So the example that I was giving in simple steps is actually the preliminary design of a real bridge of approximately that length of the span. Is a bridge which has not yet been built yet, that I designed not a long time ago, and you can see a comparison of what were the figures that were coming out from the preliminary sizing, And what were the figure after going through thousands of nonlinear analysis, but thousands of nonlinear analysis of a structure that was known. Not proceeding through a trial and error procedure, just doing something because it was similar to something else and see what happens, and then simply check if everything is working, and without considering if it's 2 times, the dimension is 2 times or 3 times, but only that it works. So very briefly, just for your curiosity, this is the bridge that I was showing with the dimension of basic dimension. These are just view of the bridge. You may be wondering why having 2 decks on the side of the pier. There are reasons for that, it's not now the time of discussing, but anyway, consider that the total width is more than 50 meters, so there were problems in having 1 single deck. And you have the design of the structure and the design of each one of the parts of the structure. And of course, you start from the foundation and you go all the way to the delicate, difficult part where you have to put all the cables to the anchorage of the cables. So the static design was going as I was discussing. It is interesting to see that if you use different codes, you have enormous differences in the level of live loads that you have to use. This dotted line down here is the Axial code, which is certainly not in line with other codes, and I'm inclined to think that at least in this particular aspect, the Axial code is not the best to be applied. And okay, this is I go fast because I have more things to discuss. But anyway, then you go through complex analysis. You see what happens for different sort of combination of live load and earthquake loading. And just to go and come back to the earthquake design of this structure, this is clearly something where you have to meet very strict performance level. You may see here that the request was to have a repairable bridge for a 2,000 year return period at a damage level. And of course, for something like this, you go through a probabilistic hazard study, and you end up, since continuing the discussion of this morning, you end up finding out that only very near-field earthquake are of some importance if you go for a uniform spectrum, for a uniform hazard spectrum. But in this case, maybe it makes sense because the earthquake are 7.5 and 8 in terms of magnitude. So it makes sense that only near-field earthquake are of some importance if the near-field earthquake is at such a high level of magnitude. And then you produce your spectral shape, and you go through some complete analysis, and you may have a look at this spectral shape here. These are displacement spectra, and this is the displacement spectrum for 30% equivalent damping, and this is the final period of vibration. Well, actually, this is the displacement demand of 1 meter, and you can see that you are essentially at the plateau level there. So you could in this case accept essentially any sort of period of vibration. And these things down here are just acceleration spectra, because this scale is giving both the displacement in meters and the acceleration in g. So at the end, you go to look at the connection between pier and deck, and you end up with a combination of hydraulic dampers that should give you approximately the properties that I was discussing in terms of equivalent damping, and therefore, since the displacement is given, the force that has to pass through them. And the things are a bit more complex than what I presented in the preliminary evaluation, because you have also to control some vertical response there that I did not discuss, and therefore you end up with some horizontal and some inclined damper. And then you go through the nonlinear time history analysis, and you end up with something which is perfectly satisfactory, and you go for the detailed design. Of course, in the upper part, you go for very refined finite element analysis to see what happens there. And you have finally the design verification. And the design verification, of course, is the phase where you could use any approach you wish, because the bridge is there. So it's not so important anymore what method you use. And you end up with checking what the displacement will be if you look in a vertical plan, considering all the three excitation in the two horizontal planes in the vertical direction. And then you check all the capacity of each one of the sections with respect to the action. And when you do something like this, you still try to have values of the forces that will anyway allow some nonlinear displacement, even if this is not the case, because you may have some unforeseen level of action. But this is another story. If you look then at what happens at the connection systems, you end up with something where you have some nice displacement loop, and you can see why it was not unreasonable to assume a 30% global damping. The reason why you could assume that is that if you look at the equivalent damping of one of these systems, you are probably at a 50% level or close by. So 30%, it's because you take into account the fact that not all the displacement and the force is passing through those elements. One final note is that for a bridge like this, but in general for any bridge, you should consider what happens during the construction phase. And I'm not saying now to consider what happens in terms of changing in the stresses and so on, which is actually an issue, but in case of what is called construction earthquake. And I think that it will be worthwhile to pay some attention on the difference with respect to the construction earthquake characteristic if you look in terms of displacement or in terms of acceleration. Because as I was discussing this morning, the displacement demand is much more affected than the acceleration demand. And as a consequence, it is much easier to cope with the construction earthquake in terms of displacement than in terms of acceleration. What I'm trying to say is that if you look at the problem of a construction earthquake in terms of displacement capacity, it's like being in a very low seismicity zone, so that only little measures, little detailing will be enough to take care of the problem. Okay, these are just construction phases. Now I would like to go to a couple of other examples to go to, under a certain point of view, simpler structure, but again to see how to deal with an isolation system. And this case that I would like to briefly discuss now in 10 minutes is the case of a viaduct in Turkey that Nigel was mentioning earlier. We have been designing together the repair and upgrading of this bridge. This was, well, maybe not a very beautiful structure, but certainly a very important one. It was a very long viaduct on the freeway between Istanbul and Ankara in the Turkish mountains, and unfortunately very close to the North Anatolian Fault, which is one of the main faults all over the world. And this bridge was actually crossing a minor fault, not exactly the North Anatolian Fault, that was not known. And it was designed for a certain level of earthquake. And it was actually almost completed. This was the situation, and we were not involved in the design at that time, when the second earthquake in 1999 came to hit Turkey. In 1999 in Turkey there were two strong earthquakes. One is more known. It was close to Izmit Bay. It was an earthquake that stopped approximately 35% of the Turkish industry and was enough to increase the inflation of 10%. So it was a very, very strong earthquake. The same year, later on in November, there was a second earthquake, which is known as the Dusce earthquake. And this earthquake was the one on this fault. And essentially, the fault was crossing the bridge at a relatively small angle, so it was not perpendicular. It was closer to be parallel than perpendicular. The angle was maybe 15 degrees or something like that. But it was just passing through the bridge. So what you see, the bridge was a very standard bridge. It had two parallel lines, one with 58 and the other with 59 spans. The spans were short spans, you see about 40 meters. You may wonder why to design such short spans in a situation like this. It is something that probably we would not do. The reason was simply to use a prefabrication plant which was nearby, and they had this deck, these beams available. And well, for me it's not a good reason, but anyway, they decided it was a reason good enough. So you had a bridge with piers that in most cases were between 40 and 50 meters tall, so that the height of one of the pier is more than the span, which makes something which is probably not very efficient from the point of view of cost. But anyway, this is not what we are discussing. They had joints every 10 piers, so joints at about 400 meters. And they had, on top of each pier here, they had 14 bearings, one for each one of the beams on one side and on the other side. And in the center of these cap beams, they had one device which was called energy dissipating unit. So imagine 14 bearings that would allow displacement, relative displacement, 200 millimeters capacity. The displacement was simply permitted through some low friction between steel and PTFE, and one energy dissipation unit with a much larger displacement capacity. This again is something that doesn't make a lot of sense, to have an energy dissipating unit which has a larger displacement capacity than the bearings. What they were thinking was that even if the bearing was going beyond the capacity, the friction was going to increase, but in a general sense the bridge could still work. Then the pier section was about 8 by 4 meters, was a hollow section, a huge section, and in fact there were no problems, as you will see. And then what you don't see here is that there was a foundation which was a height of 3 meters, and the size of the foundation, I don't remember, but it was in the range of 8 by 12 meters, something like that, with 12 piles, 1.5 meters diameter. Is that right, Nigel? Was maybe even larger than that. Anyway, not so important. There were a large number of piles with a cap beam on top of the piles that were just a little bit underground here. What happens during the earthquake? Well, you can see here, I think that you can note in the photographs there that there is a very clear permanent displacement of the deck to this direction, to the left. You can see here that this beam is penetrated on top of the cap beam, and this beam has moved out in this direction. The permanent relative displacement was in the range of 1.5 meter. And this was not a strike slip. There was a shortening of the the bridge. So the bridge was 1.5 meters shorter, essentially. And there was also a relative displacement in the transversal direction because, as I was saying, the fault was not transversal to the bridge, or not parallel to the bridge. You can see here that also in the transversal direction, you see the relation between this cap beam and this deck, and you see it here, and you will immediately note that there is a permanent displacement here, and it's also easy to see that there is a rotation here. Okay, so what happened here? These are not the displacement demands during the earthquake, this is just the permanent displacement. So these are due to the permanent displacement due to the fault movement. Relative displacement because of the permanent movement of the fault. So you have to deal with seismologists in that case, unfortunately. And you can see what happens. This is one of the beams, and this beam was resting on a bearing which was here. The bearing is not there anymore, but also you wonder how this could still stand. And this is what you see if you look from the top. And you see that there was some continuity provided by the deck, the upper deck, the one which was casted in place on top of the prefabricated beams. And on the side there was this, say, sort of beam, which was the side beam of the upper deck. And you can see here the very severe cracking of this area. And in fact, there was approximately a displacement of 300 millimeters vertically over a distance of 1.8 meter. So what I mean is that the relative displacement between this beam and the other one was approximately at a drift of 20%, which is a rather large drift, and actually is a kind of displacement that could not be dealt with just considering the standard way that we use in flexure and shear, but to explain how this part of the bridge is still there, you should look at problems in large displacement again, and considering the capacity of this part of the structure to act as an inclined strut and tie system. This is what remained of the energy dissipating unit. I will discuss tomorrow what kind of energy dissipating unit you could use, but anyway, it is a steel device that is essentially used to dissipate energy and nothing else. So it's something where you can see it here, one of them. There is something where you have steel parts that move during the earthquake and have a very uniform plasticization throughout the element, so that locally you can have maybe 40 or 45% equivalent damping, and then you will see what happens in the whole structure. Now, what was needed now? Okay, the foundation. This is the foundation that I was talking about earlier. So this is 3 meters, and these are the piles below the structure, and this is one of the piles. You can see here a very significant relative displacement. This was not extended to the whole bridge. This was actually only in 4 or 5 cases, 4 or 5 piers that were the piers that were close to the fault. Now, this is what I was trying to say: the fact that you can explain the capacity of hanging this part of the bridge only if you consider the fact that this is in large displacement, and look at what happens in terms of stratum-type system. And this was a device that we designed to raise up the bridge and be able to move the bridge of approximately 1.5 meters in one direction and also in the transversal direction, and somehow to go back to something that was similar to the original position, but not identical, because we had to shorten the bridge to the deck to make it compatible with the position of the piers. The other thing that we decided to do was to transform the deck into a continuous deck, which implied to use the empty part between the beams, which was I can't read there, which was 1.8 meter, in a transversal beam that you can see here. These are essentially the beams in the section looking in the longitudinal direction, and you could imagine here these are transversal tendons that are going from here to the other side, so that there is a continuity there. There are a number of problems if you do that, of course, because you have to deal with the changing in the sign of the bending moment, and you have to deal with temperature, relative temperature, differential temperature, and top and bottom, and so on. But anyway, the general idea was that there is no way to cope with this level of displacement capacity if you don't change completely the bearing system. And what we decided to do was to have only 2 bearings on top of each pier instead of 14 bearing plus 1 energy dissipating unit. And the total displacement capacity of these bearings was designed to be 1.8 meters in some cases and 1.4 meters in other cases, which is plus minus 90 centimeters, plus minus 70 centimeters. Now, what I'm trying to say is that, again, even if at that time the development of the displacement-based approach was not certainly at the level of today, but to deal with displacement was the key issue, to be able to design something that was effective and efficient. And in that case, what was used, and this was not really a completely technical decision, it was also a political decision, but this is not important. We used what are still called friction pendulum system, that I will discuss in some detail tomorrow, which are devices where you have some curved surface and some other, which is connected either to the pier or to the beam or to the deck, because you could use this in this direction or to move it upside down. Actually, normally they are mounted upside down because of so that no dirty, nothing will form. They will be less sensitive to dust and so on. But anyway, if you imagine that this is fixed to the deck and this is fixed to the pier, and you imagine a relative movement, when this moves, you have something which is similar to the movement of a pendulum. And therefore, you know that the period of vibration associated to this movement is only function of the radius of curvature of this surface, which is the radius of curvature of the equivalent pendulum. But since you also know that the period of vibration is the square root of the mass divided by the stiffness, you can immediately find out all the variables that you need to go ahead with the design. And this again is something that I'll discuss tomorrow when we will talk of base isolation or isolation as a whole. And this is just to conclude this, and I have only one last example to show you. This is just to show you that here there is some demolition of the internal part of the energy dissipating unit. Here we are moving the up and then transversally and longitudinally the deck. This is one of the new friction pendulum devices, and these are the connection between the existing beams and the new beam that will be casted here, including the bolts that are connected to the upper part of the bearings. And this is what happens if you look in terms of the transversal beam. These are the actual cables, and this is the position of the transversal beam. And here you can see the heads of the transversal cables. And here you can see one side of the bridge which has already been moved up, and the other one which has not yet been moved. We also decided to have the joints on 800 meters distance instead of 400 meters distance, so that we're going to reduce very significantly the problem of the joints that now had to cope with a movement of, say, 90, plus minus 90 centimeters, which is a major joint to be designed. Now, the last bridge that I want to show you is, I'm going towards the simpler and simpler things, and I will finish 5 minutes earlier or 10 minutes earlier, so there will be some time for questions if you want. Is again, I'm going down towards a simpler structure. This was a masonry bridge built at the end of the 19th century. It had serious problems, and it was closed. But on that bridge, there was a traffic of about 24,000 vehicles per day. And so there was a need of doing something extremely fast, and it was in a relatively high seismicity zone. So there were just only 5 spans of 19 meters with a width of 6.4 meters, and the thickness of the arch, the structural part of the arch here, was between about 1 meter, and the height from the riverbed was about 10 meters, and the weight on each pier was about 1,000 tons, of course, because this is a heavy structure. So if you have to deal with something like this in a high seismicity region, and you have problems of very serious damage and so on, and they ask you to do something that should be done in a very short time, and the very short time was 30 days. It's also designing it. It's a difficult task. What we did was to design a new. Of course, you cannot modify the bridge because it's it's protected, because it's monuments and so on. So what we did was to design a completely new bridge, having 2 large diameter piles drilled within each one of the existing pier, and then to have a transversal beam in the thickness of the non-structural part of the bridge, and then to have some isolator here, and then to have a deck, a concrete deck. And you see, this is the original masonry structure, and this is the new concrete structure that can work because of this isolation system. And actually, since normally you have to order isolators, and they give the devices to you in 2 months, 3 months, 4 months, what we did was the opposite, and to see what material was available. And that's the reason why there are 3 here, and we used 3 on the piers and 2 at the abutments, just to adapt the design to the available devices. But starting from the point that, for several reasons, one of them was this possible gap here, we were going to design for a displacement, for a relative displacement of 200 millimeters. So we started from the 200 millimeters, and believe me, there is no other way to design the isolation system. You can, if you start with a force-based approach, you have to start with an acceleration spectrum. And you don't know how to deal with the isolated structure. You know that years ago there were proposals to use a kind of a corrected acceleration spectrum, which was elastic at periods shorter than a certain level, and reduced because of the isolation system beyond a certain level of period, which is something that doesn't work at all. But anyway, so this is just the transversal view of the bridge. And this, I'm sorry, this is not very clear, but these are the three isolators there. These are very standard rubber isolator devices. the displacement capacity of plus minus 200 millimeters, 10% damping because the rubber used was a relatively high damping, but not so high. You could go up to 17%. I'll discuss it tomorrow. This is the vertical action on the isolators, in the sense that, of course, you don't have there the weight of the masonry structure. And it was possible to design it for a period of 2 seconds, which, of course, comes out from the 200 millimeters entering the displacement spectrum of that area. And you can see here, this is one of the transversal steel concrete beam, and this is one of the isolator which is going to be mounted here. And this is just the lower part of, the cast, the form that will be anyway left there, which is mounted on top of it. And this is what you obtain at the end. And this is a gap between the two bridges, the concrete one, which is an isolated bridges, and the masonry bridge that in this case becomes simply a reminder of the past, because there is no essentially any load on top of it. There is only the proper weight, self-weight. And in any case, if an earthquake should come, the concrete structure will work anyway, even if there should be damage to the masonry structure. So the traffic will not be interrupted anymore. And you can see that even at night you have some nice separation and distinction between the masonry structure and the concrete structure. And I stop here. I could give you as many details if you want on any one of these structures and on other structures.